In the previous video, we have learned about modeling the data structures. In this video, we will learn how to create a piece class. Think about it. We need to define rules for all of the different chess pieces. Some attributes and methods, such as color, will be common to all the chess pieces, while other attributes methods, such as rules for movement, will vary for each chess piece. First, we'll define a new piece class. This class will have the attributes and methods that are common to all the chess pieces. Then, we will define classes for every individual piece as a subclass of this parent piece class. We can then override all the attributes and methods in these individual classes. The code will look like this. Note that the piece class needs color as an argument for object creation. We create two attributes named self.name and self.color in the class. Also note the keep_reference self_model method definition. Since the piece class is nothing but an extension of the model class, we need to get a reference to the model class in this method to communicate with it. Similarly, the model class needs a reference to the new piece class. Accordingly, we add this as an import to the model class. Finally, we need a method that takes a string pertaining to the name of a given piece object and creates a new piece object. For example, we need a method that, given the arguments pawn black or simply p, dynamically creates a new pawn object with the color attribute defined as black. Accordingly, let's define a helper method in the piece.py file, but outside the piece class, which we have defined here. To support the preceding method, add the following constant to the configurations.py file. The preceding code simply takes a single character as an input. It then gets the full name for the corresponding piece class. For example, if a p is given, it gets the full name, which is pawn. It then checks the case of the character and defines the color variable as white if the input character is uppercase. Otherwise, the color is set to black. It then dynamically creates a corresponding piece object. This concludes the iteration. We have created the piece class and all of its subclasses, and we have the ability to create piece objects dynamically from a given input character. This class is simply an extension of the model class, and each of the two classes can access each other's methods by keeping a reference to each other. Displaying chess pieces on the chessboard. Now let's turn our attention to displaying all the chess pieces on the chessboard. First, we'll define a method named draw_single_piece, which draws a chess piece at the given position when it's given a position and the character representing the chess piece. The images of the chess pieces are stored in a folder named pieces_image and are named in the chess piece name in lowercase in this format. So for instance, the black queen is saved by the name queen_black.png. These images are added to the chessboard by using the canvas.create_image method, which takes the XY coordinates and a photo image object that relies on the location of the image file as its argument. We use tkinter's photo image class to reference the .png files. In addition to creating and displaying a chess piece on the chessboard, we also tag them with a custom tag called occupied. Tagging is an important feature of the Canvas widget, which lets us uniquely identify items placed on the Canvas widget. We also used the two helper methods in this code. This is just a wrapper around this code from 4.03-piece.py. Now, it's time to simply call the draw_single_piece method to all the chess pieces. A key aspect that you need to note here is that when we needed some data from the model class, say a dictionary containing all the chess pieces on the chessboard, we did not directly call the model class for the data. Instead, we requested the controller to get us the data from the model. The get_all_pieces_on_chess_board controller method is simply a wrapper around the actual method from the model class, which we can see in controller.py. Great! We now have the methods required to draw all the chess pieces on the chessboard, but mere defining does not help. These methods need to be called from somewhere. Therefore, let's define a new method named start_new_game and call it from the _init_method of the view class. In addition to calling the draw_all_pieces method, this method also resets the model via calls to two wrapper controller methods. The actual methods are defined in the model class. The reset_game_data method is simple. It just resets all the attributes of the model class to their initial states. The reset_to_initial_locations method initializes all the chess piece locations to reflect the starting position of the game. This too should be self-explanatory if you are aware of the data structure that we discussed earlier. Now, when you go ahead and run the code, the chessboard should display all the chess pieces at the starting position of the game. This completes the current iteration. The next iteration will define the rules for the movement of the chess pieces on the chessboard. We need this part done before we can think of moving the chess pieces around. Defining rules for the chess pieces. Different chess pieces have different rules of movement. Let's try to tabulate the rules. As evident from the table, the rules for all the chess pieces except for knight and pawn are pretty straightforward. Knights are different from the others. They must move 2 squares in one direction and then one more move at a 90-degree angle, following the shape of L. Knights are also the only chess pieces that can jump over other chess pieces. Pawns move forward, but they capture diagonally. Pawns can only move forward 1 square at a time, except for their very first move where they can move forward by 2 squares. Pawns can only capture 1 square diagonally in front of them. Rules for the king, queen, rook, and bishop. Let's first take a look at simple cases of orthogonally and diagonally moving chess pieces, which are the king, queen, rook, and bishop. We need to somehow figure out a way to change the position of these chess pieces by using a mathematical rule. This will show what it takes to move a chess piece from its current position, say xy, both orthogonally and diagonally. If you look at this diagram, x represents the column number and y represents the row number. It is clear that we can represent the orthogonal movements by adding to the current position the items from the tuples -1, 0, 0, 1, 1, 0, 0, -1. Similarly, diagonal movements can be represented by adding to the tuples -1, 1, 1, 1, 1, -1, -1, -1. Let's add these two tuples to configurations.py. If a chess piece can move both orthogonally and diagonally, such as the queen, the representative tuple is simply an addition of the preceding two tuples. If a chess piece can be moved by more than 1 square, it's simply a matter of multiplying the representative tuple by an integer to get all the other allowed positions on the chessboard. With this information in mind, let's code a moves_available method that, given the current position of the chess piece, the directions tuple relevant to the chess piece, and the maximum distance that the chess piece can move, returns a list of all the allowed _moves. 1. Depending on the arguments, the method collects all the allowed moves for a given chess piece in a list named allowed_moves. Number 2. The code iterates through all the locations to detect a possible collision. If a collision is detected, it breaks out of the loop. Otherwise, it appends the coordinate to the allowed _moves list. 3. The second to last line filters out the moves that fall outside the chessboard, and the last line returns the equivalent position in alphanumeric notations for all of the allowed moves. We can also define a few helper methods to support this method, which is defined here. Next, let's modify the piece child classes of king, queen, rook, and bishop. Rules for a knight. The knight is a different beast because it does not move orthogonally or diagonally. It can also jump over chess pieces. Like the rules that we followed earlier to arrive at orthogonal_positions and diagonal_positions, we can similarly arrive at the rules that are required to determine the knight_positions tuple. This is defined in 4.04-configurations.py. Next, let's override the moves_available method from the knight class. 1. The method is quite similar to the previous superclass method. However, unlike the superclass method, the changes are represented to capture moves using the knight_positions tuple. 2. Unlike the superclass, we do not need to track collisions because knights can jump over other chess pieces. Rules for a pawn. A pawn has a unique movement too, in that it moves forward but it captures diagonally. Let's similarly override the moves_available class from within the pawn class. Number 1. we first assign the initial _row_position direction and enemy variables depending on whether the pawn is black or white. 2. Similar to the previous moves _allowed methods, this method collects all the allowed moves in a blank list named allowed _moves. 3. Then we collected a list of all the prohibitive moves by concatenating two lists of squares occupied by all the black and white chess pieces. 4. We defined a variable named forward, which holds the position of the square immediately ahead of the current position of the pawn. 5. A pawn cannot move forward if there is a chess piece in front of it. If the forward position is not prohibited, the position is appended to the allowed _moves list. A pawn can move 2 places forward from its starting position. We check whether the current position is the starting position, and if it's the starting position, we append the double down move to the allowed _moves list. 1. A pawn can capture only the diagonally adjacent chess pieces in front of it. Therefore, we assigned a variable attack to track the diagonally adjacent positions on the chessboard. If the diagonally adjacent square is occupied by an enemy, that position qualifies to be appended to the allowed _moves list. 2. Then we filtered the list to remove all the positions that may fall outside the chessboard. The last line returns all the allowed moves as a list of corresponding alphanumeric notations, as we did in all the previous definitions. This completes the current iteration. We coded the logic needed to enforce the rules related to the movement of chess pieces on the chessboard. The movement validation of chess pieces. Before we allow chess pieces to move, we must have a record of all the possible movement options on the chessboard. At every move, we also need to check whether it is a legitimate turn for a given player, and the proposed move should not cause a check on the current player's king. Now, a check may occur on the king not only from a chess piece that was moved, but from another chess piece on the chessboard as a consequence of such movement. Thus, after every move, we need to calculate the possible moves for all the chess pieces of the opponent. Accordingly, we will need 2 methods to do the following. 1. Keep a track of all the available moves for a player. 2. Check whether there is a check on the king. Let's add 2 new methods in the model class. Tracking all available moves. The code needed to keep track of all of the available moves for a player is 1. We have already coded the moves _available method in the previous iteration. 2. This method simply iterates through every item in the dictionary and appends the moves _available result for every chess piece of a given color in a list named result. Finding out the current position of the king. Before we code the method that checks whether a king is in check, we first need to know the exact position of the king. Let's define a method to find out the current position of the king. This code simply iterates through all the items in the dictionary. If a given position is an instance of the king class, it simply returns its position. Checking whether the king is in check. Let's define a method to check whether the king is in check from the opponent. 1. First, we obtain the current position of the king and the color of the opponent. 2. We then found out all the possible moves for all the chess pieces of the opponent. If the position of the king coincides with any position from all the possible moves, the king is in check, and we return true. Otherwise, we return false. This accomplishes the objectives for the iteration. We are now in a position to check all the available moves for a player at a given point in the game. We can also check whether a king is in check from the opponent. Awesome! In this video, we have successfully learned how to create a piece class. In the next video, we'll see how to make the game functional.